Now we're going to take a look at the E2 elimination. E2 stands for elimination bimolecular. That tells us that there's two species in the rate determining step similar to SN2. With the E2 reaction, everything happens in a single step. That means there's no carbocation rearrangement to worry about. And what we end up doing is eliminating a beta hydrogen and a leaving group. So let's look at our example and see what the beta hydrogen is. The chlorine's a leaving group, and it's attached to this carbon here. The carbon the chlorine's attached to we call the alpha carbon. And then any carbons attached to that carbon are called beta carbons. So we have a beta carbon here and a beta carbon here. Then hydrogen on that beta carbon, those are beta hydrogen. So this has two beta hydrogen, this has two beta hydrogen. In this example, both of these carbons are equivalent, so it doesn't matter which one you choose to do the reaction with. So if I take my hydroxide as a base, I'm going to go and draw an arrow to the beta hydrogen, then I'll push the electrons in that CH bond down to form the pi bond, and then lose my leaving group. So everything happens in a single step, and the products we end up with are the alkene plus water plus my chloride leaving group. The reaction rate we said already was bimolecular. It's going to be the rate constant times the concentration of your organohalide times the concentration of your base. Now, in the case of E2, the strength and concentration of base is very important. Here we're going to look at the Regio selectivity of E2 elimination like we did the E1. So we already know that the Regio selectivity is just saying which hydrogen do we eliminate. In this case, the answer actually is that it depends on the base that you use. So what we're going to do is look at an organohalide and reaction with two different bases, and we'll look at the different products that we can get. So the organohalide we're going to use is just 2-bromobutane. And I'm going to draw this twice so we can use it with each of our bases. The two bases we're going to look at using include the first, which is tert-butoxide. So it's oxygen with a tert-butyl group on it. This is a very large, bulky base because we have all of these carbon groups. Some other ways you might see this written, you might see it written as just OT-butyl minus as an abbreviation. You might see it written as NaOTBU, or sometimes you'll see it written in more of a condensed form, where you have O, C with 3 methyls on it. All of these mean the exact same thing. If you see that, think bulky base. In the second example, I'm just going to use hydroxide, which is a very small molecule, so that's a small base. And of course, this could be written as sodium hydroxide. And just to give you some other small bases to be aware of, you could have things like OCH3 minus, NH2 minus, other amines. There's ethylamine, even other oxygen bases. Really, for our purposes, anything other than tert-butoxide we'll consider a small base. Looking back at our organohalide, we see we have the alpha carbon where the halogen's attached, and we have two beta carbons. In the case of the bulky base, what you want to think about is how accessible are the hydrogen on those carbons. With the beta carbon on the right, we just have these 3 free methyl groups here, easily accessible. The beta carbon on the left, it's not that it's too hindered, but still, there's more going on over here. These aren't as available. So what that means is this bulky base is going to prefer to react with the methyl hydrogens. When we do that, we'll eliminate one of those, and the product we get is this alkene. This is called the Hofmann product. It's named after the chemist that studied eliminations to give the less substituted alkenes. So again, the bulky base attacks the beta hydrogen on the most accessible carbon to give the least substituted alkene. So just remember, bulky base is going to give the least substituted alkene. So now if we go to the small base actually has a preference for the more substituted, the hydrogen on the more substituted carbon, and this has to do with product stability. So here's a beta hydrogen on that carbon. Small base will come in and take that and eliminate. And we do prefer the trans double bond over the cis. And this is called the Zaitsev product. So the small base attacks the beta hydrogen that gives the most substituted, most stable carbon-carbon double bond. So the thing to remember here is, in the case of a small base, you want the most substituted alkene product.